Hey, it's Ben, and welcome to Lecture 2 of Open Project Space. We're going to talk about integrated circuits and the troubleshooting equipment and techniques we use to debug our circuits. And now we have to begin with a long-awaited discussion on circuit analysis and circuit topology. And so I think, of course, we should start by redefining what a circuit is. Remember from the first lecture, a circuit is a closed loop path where electrons can flow. And now we extend this conversation to include new ways to describe our circuit. We can decompose our circuit into branches, nodes, and loops to analyze the voltage, current, and resistance across the segments of our circuit. Now, why do we do this? Well, circuit analysis will enable us to design circuits and debug and test the performance of the circuits. And as you will find in your future projects, it is extremely critical to develop these debugging skills and a solid understanding of circuit analysis so that when you come across a problem in a circuit, when there's an unknown issue, you have the tools you need to resolve it. So that brings us to our first term. Now, a branch is a two-terminal circuit element. Take the schematic below, for example. We have a voltage source and a couple of resistors. And I'm going to highlight for you the branches in this circuit. Remember, it's a two-terminal circuit element, so that means our voltage source and every resistor counts as a branch. And I included some other symbols for you to consider here. These are all two-terminal circuit elements, so they count as branches. Whether it's an LED, a motor, battery, voltage source, it's all the same. They're branches. Now, building off of that, we have nodes. A node is a connection between two or more branches. So take a look at the schematic here. It's the same as on the previous slide, but now we've highlighted our nodes, our connections between branches. Here we have three distinct nodes. We have one on the left. It's a connection between the voltage source, the resistor here, and the resistor here. That's the green node. We have another node, a distinct node. It's a connection between these three resistors. And we have one last node, this red node, that's a connection between the three resistors and the voltage source. Now, a really important concept to understand here is that when you are on the same node, regardless of which point on the node you're at, whether it's here near the voltage source or here near that resistor on the far right, they have the same voltage and the same current. Again, all points on the same node have the same voltage and the same current. Okay, now I have a comprehension question for you. Taking a look at the schematic here, we have 1, 2, 3, 4, 5 resistors that are all connected through this region here. What is the voltage between this point and this point? Take a moment to think about it. Pause the video right now. All right, we're unpausing. So the answer is there is no voltage between these 2 points. And why? These points lie on the same node. This is one connection between this resistor here, this resistor on the right, the two resistors on the bottom, and the resistor on the left. This is one connection and one node. And again, how do we identify this as one node? Well, there are no branches in between. There are no circuit elements dividing this connection. And because it is purely just a connection between these 5 resistors, these 5 branches, this is just one node. And again, between any 2 points on a node, there is no difference in voltage and no difference in current. All right, moving on. We have wires that you used on your project before to build an LED circuit. Now, wires we can treat as nodes, as long as we assume that the wire has no resistance and no voltage change across it. And while this isn't technically true, and there are conditions in which you cannot ignore the resistance or the voltage change across the wire, for our projects, those conditions are negligible. So again, we can treat wires as nodes, as connections between our branches, our circuit elements. Think about the breadboards we discussed in Lecture 1. Think about the breadboard that you used in the project that accompanied it. Now, a breadboard strip, those 5 holes on one side of the channel, these 5 holes can be considered a single node. Why? Because they're connected electrically inside the breadboard, and there are no branches that divide them. And so, again, it's a single connection, a single node. Now, what happens if we were to connect 2 strips via jumper wire over that channel that electrically isolates either end of the breadboard? Well, if we connected via jumper wire, remember we considered wires to be nodes, then we've created one large node, a 10-hole node, a node that contains 2 strips across the breadboard. So we've talked about nodes, we've talked about branches. Now we need to explain voltage drop. It's the decrease of electric potential, the decrease of volts along the path of current flowing in a circuit. Now, why is voltage drop important to us? Well, we said that nodes connect 2 or more branches. And so that means between any 2 nodes, there must be a branch. There must be a circuit element. And often in our circuit analysis, we want to find the voltage drop, the decrease in volts across that circuit element. Now here's an example for you. Consider the last lecture where we wanted to identify the forward voltage across a LED. Now, forward voltage happens to be similar enough that we could describe it also as the voltage drop from the positive to the negative terminal of an LED. And it was important in our discussion to identify the voltage drop because that determined what resistor we would need to use so that we wouldn't exceed the maximum current that could flow through the LED before that LED burnt out. Now I'm going to show you how to calculate the voltage drop across a branch. Here we have a simple resistor, which is our branch, and on either end of the branch we have a node. On one end we have a node whose voltage we've measured to be 10 volts relative to some reference point, which is not seen in this schematic. On the other end we have a node whose voltage was measured to be 4 volts. And we've been tasked with finding the voltage drop across this branch, across this resistor, which is VR. And now we can divide this into a number of steps, the first of which will be to determine the sign of the voltage drop. And remember from the previous slide, I said we will use the direction of current and the reference polarity to help us determine whether or not the voltage drop will be positive or negative. And so again, that's our first step. But before we proceed, we need to pause and discuss something. We need to talk about the sign convention of a branch's voltage drop. As a very important note here, in circuit analysis, the current's direction through a circuit and a branch's voltage drop reference polarity are arbitrary, meaning you can define the reference polarity of the branch's voltage drop to be either of the following. You could have a situation in which the current flows from the positive to negative terminal of the reference polarity, or current flows from negative to positive. Now, note the difference in my phrasing between the voltage drop's reference polarity and the actual branch's reference polarity. A resistor is not a polarized component. The resistor itself has no polarity. But when we calculate voltage drop, we define a reference polarity. And the reference polarity, in reference to the current direction, affects the sign of the voltage drop, whether it's positive or negative. And the only rule here is that you have to be consistent. Once you define your reference polarity, once you define your current direction, you can't change them, especially between calculations, or you're going to get the wrong answer. I'm going to give you two simple rules for how we determine the sign of the voltage drop. The first rule is, if we have a branch where we've determined the current to flow from the positive to negative terminal of its voltage drop, then the sign of the voltage drop will be positive. Now for the second rule, if we have a branch where the current flows from the negative to positive terminal of the voltage drop, then we take the sign of the voltage drop to be negative. Let's apply that to our example. Step 1, again, we determine the sign of the voltage drop across our branch, the resistor. We do so by defining the direction of current and defining the voltage drop's reference polarity. We're going to define the direction of current to flow from the node whose voltage is positive 10 to the node whose voltage is positive 4. Now this is just intuitive because conventional current flows from a place of higher electric potential to a place of lower electric potential. And again, I need to remind you that we could have just as easily defined current to flow bottom to top from 4 volts to 10 volts. It would have changed the sign of our voltage drop, but as long as we were consistent, the final calculation would be correct. Again, I realize that's weird to wrap your head around right now, so bear with me. To recap, we defined the direction of current to flow from the 10 volt node to the 4 volt node. And we defined our reference polarity such that the current flows from the positive to negative terminal of our voltage drop's reference polarity. And remember our rule, if current flows from positive to negative, then the sign of the voltage drop will be positive. Now for the next step. We're going to calculate the voltage drop across the resistor as the difference in volts between terminals. And we do so by following the direction of current. Okay, so that would mean then, if we're starting at the node on this side of the resistor, following the direction of current, we take 10 volts minus 4 volts. You see that right here, 10 volts minus 4 volts. And we perform some basic arithmetic and find that the voltage drop across the resistor is 6 volts. All right, it's your turn. You will find the voltage drop across this resistor, across this branch, using the given reference polarity. So you'll notice this example is very similar to the one before, but we've changed a couple things. The voltage at this node is now -7, and the voltage at the opposite node is -2. And we've done something a little tricky. We've changed the reference polarity such that current now flows from the negative to positive terminal of the voltage drop. So go ahead, pause the video. Again, I understand if these concepts haven't quite set yet, so go ahead, rewind if you need to, come back to this clip, attempt the problem, and unpause when you're ready. All right, let's discuss the answer. So again, the first step is to determine the sign of the voltage drop. Remember our two rules. In this situation, we have current flowing from the negative to positive terminal of the voltage drop's reference polarity. If current flows from negative to positive, we'll take the sign of our voltage drop to be negative. The next step is to calculate the difference in volts between the two nodes of this branch flowing in the same direction as the current. So that would be -7 minus -2. -7 minus -2 is -5. We're almost there though. Remember, we need to apply our sign. So if our difference in volts was calculated to be -5, but we decided that the sign of the voltage drop is also negative, we need to take the opposite value of -5, and that's 5. So our answer is B, 5 volts. The voltage drop across the resistor is 5 volts. Now, I have another way for you to look at this. If you're still struggling a little bit to understand the concept, and I admit that's partially on me, so I'm looking for different ways to explain it. Let's take a look at that reference polarity. Remember our discussion about voltage in the previous lecture and how voltage is measured so that when you measure it at a specific point, it's in reference to another point. We have our polarity here of our voltage drop. What we're doing when we calculate the voltage drop is we're actually measuring the voltage of the positive terminal relative to our reference point, which is the negative terminal. And so if the positive terminal here is -2 volts, and at a reference point, the voltage is -7 volts, then when we calculate the voltage of the positive terminal relative to the negative terminal, the difference in volts from the positive terminal to the negative terminal, it's -2 minus -7. -2 minus -7 is 5 volts. So again, that's a different way of looking at it. That might be easier to understand. It might be more challenging. So you can fall back to that concept that we explained on determining the sign of the voltage drop based on the direction of current and the reference polarity. Or you can use this other example, this way of thinking through the problem that I described to you just now. All right, moving on. We've talked about branches, we've talked about nodes, and that third concept to wrap up our discussion of circuit topology is going to be loops. Now, a loop is a closed path through our circuit elements. A loop starts at any node and it must end at the same node. That is what a closed path is. Now, as a second rule, the loop cannot pass through any node more than once. So let's take a look at that same schematic that I showed you at the beginning of the lecture, and we are going to define some loops. We have a loop here. It flows through these two nodes, one side of the voltage source and resistor, and the other side, these two nodes. We have a second loop here. It flows between 3 nodes, one here, one here, one here, and it ends at the same node it started at in a loop. We have a third node. Same concept, it flows from this node at the top to this node at the bottom and then back here. We can keep on going. We can define a loop that encompasses the entirety of this circuit. It starts at this node here, flows across to this node, then the node at the bottom, and then completes at the same node in the top left corner. We can actually define 2 more loops. We can define a loop that encompasses the nodes which are held by loop 1 and 2. That would be a loop starting at the voltage source's positive terminal here, this node, flowing over to this node, down here to the node at the bottom, and back up to the top. We could define a loop that encompasses the nodes of loop 2 and loop 3. Let's say we start at the bottom node here, we flow up to the node in the top left corner, then to the top right corner, and then back to the bottom. So that actually gives us 6 loops in this one circuit schematic, only 4 of which I've shown here, just so that things aren't overlapping and making the point unclear. Building off of these concepts of loops and nodes and branches, we have series and parallel circuits. Let's start with series. 2 or more circuit elements are in series if they exclusively share a single node. So take this circuit, for example. We have 3 elements here, which are incandescent bulbs. Remember, elements are the same as branches. These elements are in series. Why? Because these 2 incandescent bulbs, the one here on the right, the one in the middle, share a node exclusively here. The one in the middle also shares a node exclusively with the incandescent bulb on the left. In fact, the entire circuit is in series because this battery, yet another circuit element, exclusively shares a node on the left with this left incandescent bulb. The same is true for the incandescent bulb on the right. It exclusively shares a node with the battery's negative terminal. And so, and here's the cool thing, if the circuit elements are in series, they carry the same current. We have, let's say, a 20 milliamp current flowing out of the positive terminal of the battery. That 20 milliamps flows through each incandescent bulb as well. It's the same current, and it flows all the way back to the negative terminal of the battery. Okay, so now parallel circuits. In parallel circuits, two or more elements are parallel because they are connected to the same two nodes. Let's take the diagram here as an example. We have a battery and two incandescent bulbs. On the right side, the right terminals of each of these circuit elements, they share a node. On the left side, they also share a node. That means they share the same two nodes. They're parallel circuit elements, the battery and the two incandescent bulbs. Now, the cool thing about parallel circuit elements is that they have the same voltage across them. So let's say this battery is 1.5 volts. That means at the positive terminal, there is 1.5 volts relative to the negative terminal. That also means, because the battery is in parallel with the two incandescent bulbs, that there is 1.5 volts running across this incandescent bulb and also 1.5 volts across this bulb as well. The same voltage across each circuit element. Now let's apply that concept of series and parallel circuits to resistors, because we can actually derive a single equivalent resistance from multiple resistors when they are in series or parallel. We can reduce the complexity of our circuit schematics when we have resistors in series or parallel. Now, these are pretty basic equations. Let's take, for example, 3 resistors in parallel. The equivalent resistance can be found by taking the reciprocal of each resistor's value, adding them together, and it's equal to the reciprocal of the equivalent resistance. For resistors in series, shown over here, resistor 1, resistor 2, resistor 3, we just add the resistor values, and that becomes our equivalent resistor. And so the gist is, these 3 resistors in parallel can be replaced with one equivalent resistor of this value. And for these 3 resistors in series, they can all be replaced with one resistor of this value. Let's see this in action. We're going to use some example problems. First, let's talk about some resistors in series. Given that R1 is 10 ohms, R2 is 30 ohms, and R3 is 70 ohms, we can find the equivalent resistance. Let's plug and chug that formula we saw on the previous page. R equals R1, R2, R3. So we plug in our values. We're going to add them together. 10 plus 30 plus 70, that gives us 110 ohms, which is our equivalent resistance. Pretty simple. Let's throw an example of resistors in parallel at you. Given the same resistor values, 10 ohms, 30 ohms, and 70 ohms for the resistor 1, resistor 2, and resistor 3, respectively. Let's find that equivalent resistance. We take our parallel resistor equivalence formula. We plug in our numbers, add these together, chugging our values. We get this nasty number, but we're going to take the reciprocal just to finish up this equation. We find that the equivalent resistance is this ugly fraction, which we're just going to convert into a decimal. It's around 6.77 ohms. There you go. We've talked about circuit topology. We've talked about finding the voltage drop across a branch. We've talked about series and parallel circuits. It's time to discuss the meat of circuit analysis. That is Kirchhoff's laws. There are 2 of them. We're going to start with Kirchhoff's voltage law, or KVL. Kirchhoff's voltage law states that the sum of all voltage drops in a closed loop is equal to 0. Looking at the circuit diagram on the right, we have one closed loop, and lying on that loop is a battery and 3 resistors. And we will find when we apply KVL to the schematic that the voltage drop across the battery plus the voltage drop across these 3 resistors is equal to 0. The sum of all the voltage drops in the closed loop is equal to 0. We can derive many equations just from this one law, KVL. And so now let's apply it to what should be a familiar circuit at this point, a simple LED circuit. We have one closed loop with a battery, a resistor, and an LED. We're going to use Kirchhoff's voltage law to solve for the value of R1. What's the use case? Remember, when you're building a simple LED circuit, you have a battery and you have an LED. Now you know the voltage of the battery, you know the voltage of the LED, you know the recommended current that should pass through the LED, and that recommended current you will set based on the resistor value we'll choose, because the higher the resistance, the lower the current, the lower the resistance, the higher current flowing through the closed loop. We can use KVL to solve exactly that resistor value. So the first step is to determine the current direction and the reference polarity of each component's voltage drop. We'll define the current to flow in a clockwise fashion around the loop, and we'll define our reference polarities to be consistent with the true polarity of each component, meaning that this battery already is polarized. Its positive terminal is here, its negative terminal is here. So when you define its voltage drops reference polarity, we'll do the same thing. Positive terminal here, negative terminal here. Same applies to the LED that is already a polarized component. We'll set up its voltage drops reference polarity such that its positive terminal is on the true positive terminal of the LED and the negative terminal of the reference polar. The negative terminal of the reference polarity is on the negative side of the LED. As for the resistor, which is a naturally unpolarized component, we've defined our reference polarity to follow the direction of the current. So current flows from the positive to negative terminal of the resistor. And you'll see why this can be an optimal decision when we create our equation for the voltage drops in the loop, which is our next step. Let's create that equation. So again, the reason why we determine the current direction and the reference polarities first is because that dictates the sign of each voltage drop. Now, in order to determine those signs, at last we will follow the direction of current through each component. We find that for this resistor, current flows from the positive to negative terminal of the resistor's voltage drop. That creates our first variable in our KVL equation, positive VR1. Now we're going to continue. Current's flowing to our LED. It flows from the positive to negative terminal of our LED. So we're going to add the voltage drop of the LED. It's positive value again, positive to negative. And now we approach, as our current flows through the battery, we approach the negative terminal first. And so current's flowing from the negative to positive terminal of the battery. The voltage drop across the battery is negative. We're going to subtract V battery. So we've created our equation now. VR1 plus VLED minus V battery is going to be equal to 0. And now we plug and chug. We solve the equation for R1. What we do is we plug in our values. Now, this should look familiar. We're going to substitute VR1 with I times R1, the current through the loop times the resistance of the resistor. This is Ohm's law, V equals IR. This is a valid substitution. And we're going to replace our other variables, VLED and V battery, with their true values. The voltage of the LED is 3.2 volts, and the voltage of the battery is 9 volts. Now, as our next step, we substitute the current variable and the resistor variable. We know the current through the loop has to be 20 milliamps, and we don't know yet the value of the resistor. So, in fact, we won't substitute this for anything yet. This is the value we're solving for. We have all of our knowns plugged in and one unknown variable. So we solve for our unknown. We get the resistor value as 290 ohms. And this should be very familiar at this point because this equation was actually provided as part of the LED circuit project. So you could determine the unknown resistor value which you would use to build your circuit. All right, your turn. You are going to find the value of R1 in the circuit below. This is the same circuit as in the previous slides. We've just changed the values. So go ahead, pause the video, rewind it if you need to, recap what you must, attempt the problem, and then unpause. All right, this time, no solution will be provided. The math is identical to the slides before, so go and reference those to confirm your answer is correct. Now for Kirchhoff's current law, or KCL. Kirchhoff's current law states that the sum of currents entering a node is equal to 0. In other words, the current entering a node is equal to the current exiting a node. Take, for example, the schematic on the right, this node right here. This node connects R1, R2, and R3. We find that the current passing through R1, which is I1, as it enters this node, is equal to the current exiting the node. The current exiting the node is I3 and I2. And so we find that I1 is equal to the sum of I2 and I3. The current entering the node is equal to the current exiting the node. Now we won't do an example problem for this, but make sure to keep this concept in the back of your mind as you work through circuit debugging in the future. Which leads us to our next major discussion, multimeters. Multimeters are fundamental to any troubleshooting or debugging you do with circuits. Multimeters are instruments which are used to measure the electrical properties of a circuit. This includes voltage, this includes current, resistance, continuity, and the fancier your multimeter becomes, the more properties you can measure. Today, we typically use digital multimeters or DMMs as opposed to analog multimeters. There are two main varieties of digital multimeters. There are the manual ranging multimeters, and there are the auto ranging multimeters. Now, the first of which, the manual ranging one, requires the user to manually select an appropriate measurement range. Now, you can just see from a glance that this is going to be less convenient for quick use. There's more going on this dial compared to the auto ranging multimeter. But the benefit is, and especially for people entering as hobbyists into the world of electronics, is that manual ranging multimeters are often less expensive than auto ranging multimeters. Now for the auto ranging multimeter, you can automatically select the measurement range, and the user only needs to select the measurement type. It might be voltage, it could be amperage, resistance. We're going to cover all of these. Now, the multimeter has two probes which interface with the circuit. The first is the red probe, and we also have the black probe. Now, the red probe is associated with the positive side of a component or connection. And generally, you're going to plug it into the port on the digital multimeter that's labeled volts, ohms, milliamps. Now the black probe is associated with COM, and you're going to plug it into the COM multimeter port. What does COM mean? COM, or common, is the reference point from which the red probe measures the voltage, current, and so on. Now, just to avoid confusion down the road, common is not the same as ground. So how do we measure DC voltage with an auto-ranging multimeter? Well, the first step would be to connect your probes to the multimeter, and then you would set the dial of the multimeter to DC voltage. Now notice how there are two V symbols. The reason why DC voltage has a straight line above it is because that is the symbol for DC current, whereas the oscillating wave represents AC current. This is for measuring AC voltage. So set your dial again to DC voltage. Now you would place the red probe on one node and the black probe on another node to be used as the reference point, because remember, black probe is COM, COM is the reference point. Then you read the display, because the display value will be the voltage drop from the node at the red probe to the node at the black probe. Now let's see that in action. I've got here the classic LED circuit. It's supplied power by a 9-volt battery. We've got our auto-ranging Radio Shack multimeter right here. Now, in this multimeter, there aren't multiple symbols for AC and DC voltage. They're combined and they're set via one of these buttons, select. And so this is even simpler. We're just going to set the dial to the 1 voltage symbol, and then we're going to take our probes, red probe, black probe, and we're going to apply the red probe to the positive end of this LED and apply the black probe to the negative end of the LED. What you should see on the display is the forward voltage of our LED. Now this LED is supposed to be somewhere around 3.2 volts, and the reading we're getting is around 2.9, which is pretty darn close. So this is how you would confirm the forward voltage of your LED. Next, we'll talk about measuring resistance on the auto-ranging multimeter. Big surprise. First thing you're going to do is connect your probes. Then you're going to set the dial of your multimeter over to the ohm symbol. And now, as a next step, you're going to disconnect your component, your resistor, from the live circuit. Now, why do we do that? Well, in this test, the multimeter actually supplies a small amount of current through the resistor that you're measuring so that it can determine its resistance. We don't want to apply any change in current to our live circuit because we didn't design the circuit most likely to accommodate that kind of change. So it's much safer to disconnect the component from the live circuit. Now, just as before, we're going to place a probe at each terminal of the component, and then we'll read the display. Let's see this in action. So again, I have the auto-ranging multimeter. I have the same LED circuit, but I actually disconnected the resistor from the circuit. So now it's just standing alone, and so it's ready to be measured. First step, connect your probes. Second step, set the dial to ohms now. And as our third step, again, disconnect the resistor from the live circuit. We take our probes, we take the red probe and apply it to one side of the terminal, the black probe, apply it to the other side. And we should be reading a value of somewhere around 430 ohms, which happens to be the value of my resistor. Easy enough, right? Now, you might also want to measure DC current with your auto-ranging multimeter. The first step, as always, is to connect your probes. The second step is to set the dial of the multimeter to the DC amps symbol, the DC current symbol. And then, and this is a little different from the other ones, you're going to place your probes in series with the components in the circuit. because basically what we're doing is adding the multimeter as though it were a component in series with the circuit. It's going to read the current flowing through it as though it were just a node between two of our components. And so it should have little effect on the circuit, assuming we place the probes in series. And then as usual, we read the display. Let's see this all in action. So we've got our classic LED circuit. This time the LED is not lit. Why? Because I've moved the resistor to a different strip from the positive terminal of the LED so that the circuit is currently disconnected. And this is so we can take our probes and connect them such that the multimeter is in series with the circuit. Now, the first step, as always, is to connect our probes. I put black where COM is, but I have a note on the red probe in this case. Now, typically when you're measuring current, you'll want to pay attention to the amount of current you're measuring. You can use the VΩm's milliamps port. On this particular multimeter, if you're measuring up to 400 milliamps max, if you're measuring more, you have to switch to the 10 amp max port. Now, generally multimeters will note right below the port or around the port what the current rating is. On this particular multimeter, oddly, even though we're not measuring anywhere close to 400 milliamps, it prefers the 10 amp port. Next step is to set the dial. Here on this multimeter, I have 2 amp symbols, 2 DC current symbols. One is actually for microamps and the other is milliamps. We're measuring on the milliamps level because we're expecting around 15 to 20 milliamps of current to run through our LED circuit. Now it's time to test it with our probes. We're going to take one probe, apply it to the positive terminal of the LED, take our other probe and apply it to the terminal of the resistor, and look at that. We've got light, and the circuit's current seems to be around 13 milliamps. There you have it, measuring DC current. Last but not least is the continuity test. You can test continuity with your auto-ranging multimeter by again plugging in the probes. Then you're going to switch your dial to the continuity symbol, which looks like this, after which you're going to disconnect your power source from the circuit. You'll place your probes on the circuit, and if the multimeter beeps, you know there is a continuous path between the two probes. Now let's take that multimeter for a spin. We're going to test continuity on that same LED circuit. Remember, our first step is going to be to connect the probes. I'm actually going to move this probe back to our classic VΩm's milliamps port. The next step is going to be to set our dial to continuity. There we go. And I'm going to disconnect our power source. Now, the important thing to note here is you're really testing for continuity on the same node. If you test for continuity across a component with a resistance, you might not hear a beep, even though technically current can flow through the component. So again, the application here is to take your probes, apply them to 2 points on the same node. Again, at any point on a node, you should have no voltage loss and continuity current flow. Otherwise, you have issues. So we'd expect, since the resistor is in the same strip as the LED, for there to be continuity between this positive terminal of the LED and this resistor. So we should expect a beep. There we go. Hopefully you can hear that. Now we would also expect continuity between this wire here and this negative terminal of the LED. There we go. That's basically how a continuity test works. Now, let's say you expected this resistor here to be connected via the same node as this jumper wire. So I'll place one probe here and one probe here. Now we don't get a sound. That means there's no continuity between these 2 points. If it was your expectation for that to be true, you know you have issues now. So that's the gist of the continuity test. Now that you've learned how to use multimeters, let's talk about the general process that you can use for troubleshooting circuits. We can break down this step-by-step process into two major components. The first of which is to find the issue on your circuit. The second is to verify that issue. Once it's verified, you should know how to fix it. So, as a first step of finding the issue, you want to do a quick check of your power supply and the ground. It's very easy to poorly connect the terminals of, say, your battery to the rest of your circuit. So performing a quick check here to make sure that the power supply is providing the correct voltage, to make sure that the power and ground connections are made properly to the circuit, will save you some time if it turns out to be a small issue there. How do I check to see if the power supply is providing the correct voltage? You can use your digital multimeter to measure the voltage. Let's say you have a 9-volt battery. That 9-volt battery is expected to provide somewhere between, say, 8.5 and 9.2 volts. If it starts going below that, you might be in trouble. So if you measure the voltage across the terminals of your battery and you find it somewhere near 7 volts, that battery's dead. It needs to be replaced. So bam, you found the issue. It's your voltage source. Now, let's say the power supply and ground check works out. Everything looks okay. You're going to visually inspect the circuit now. Look for loose connections, potentially damaged components. If you have soldered something to a perf board, look for cold solder joints, stuff like that. Things that are very easily to find via a quick scan of the circuit. In fact, if that quick scan is insufficient, or you found a connection that looks a little bit sketchy, you can use your digital multimeter for a continuity test. Test the continuity of that connection. If it beeps, you're good. If it doesn't beep, that connection is too loose. It needs to be redone. Now let's say your visual inspection of the circuit passes. You have to do two more things to make sure everything is running. And if you get to the bottom of this list and your circuit still isn't working, you might have to start back at the beginning and re-examine. You may have missed something. So the third step would be to verify the schematic diagram. You got to make sure you understand what the circuit is actually supposed to do. In fact, maybe you expected the circuit to do something different from what the actual schematic said it would. And in fact, the circuit was working the whole time, you just didn't understand it quite right. Or, when you verify your physical circuit design in step 4, you find that the circuit doesn't actually match the schematic diagram. When you verify the physical circuit design, you should go node by node, branch by branch, and make sure every component is properly connected. You can actually check the component values against the schematic as well. For example, the schematic says you should have a 430 ohm resistor somewhere in the circuit. You can use a digital multimeter to measure the resistance across that resistor in your physical circuit design to make sure that the values match the schematic diagram. At this point, ideally, you would have found the issue. Now that you've found the issue, the potential issue, you need to verify it. It's not enough just to say, I think this component is broken, let's replace it. You need to make sure that that component was actually broken. So, of course, we're going to start with, if you suspect that there's a faulty component, replace the component and immediately test the circuit. If the circuit still doesn't work, you should then test the faulty component on a working circuit. Maybe you have a second copy of it, or there's somebody you know who's also working on this circuit. If it's possible, test the component on a working circuit. If the suspected faulty component works on another circuit, then you know that wasn't the issue with your original circuit. You should try to identify a new one. Now, if the suspected faulty component doesn't work on the other circuit, then you should be relatively confident that that component is actually broken, and you should use the replacement component. However, there's still work to be done. You got to this point in the instructions because the circuit still doesn't work, but you did find that the component was also faulty. This indicates that you have more than one issue. So go back to these steps on how to find potential issues, and hopefully you will uncover another one there. Okay, let's say you found the potential issue to be a poor connection, say a loose wire. You verify it by resoldering or replacing the connection as needed. You replace the jumper wire, you replace the breadboard, maybe the breadboard is faulty, or you resolder the joint. Test the circuit again. If the circuit fails, test the connections again with the multimeter. Perform a continuity test. With soldering, it's very easy to resolder twice or thrice and still have the joint soldered just as poorly as the first time. That's about it on the basics of circuit troubleshooting. It's a very trial and error process. If you can follow any sort of steps, even if you define them on your own, that more methodical approach will aid you better than rapid fire and random guesses as to what's wrong with your circuit. Good luck. Now for our last big discussion of the lecture, integrated circuits. An integrated circuit, or IC, chip, microchip, they're all the same. It's a set of electronic circuits that are laid out on one small flat piece of semiconductor material. Now, the electronic components are integrated on the chip. That's where the term integrated and integrated circuit comes from. This enables us to take complex circuits like in the diagram shown here and scale them down to what ends up being a minuscule sized components. This is the IC, chip, microchip, integrated circuit. Again, all the same name. It can be scaled down and mass produced. This is a lot easier to work with on a breadboard circuit than, say, this discrete circuit if you were to lay out every component by hand. Every integrated circuit has a specific function or set of functions, as well as a layout of its pins, which are specified in, it's all coming back already, a data sheet. Now, the IC will also typically have some sort of notch, or in this case, a dot that indicates its orientation. So for this particular IC, the notch is in this corner, and the notch lies just to the right of the pin labeled 1. So if you were to then reference the data sheet, you would look somewhere and find the pin function table, which is going to list the pins, what they do, and their numbers. Again, the notch will help you identify the pin number on the table relative to the physical design, as well as this pin layout diagram or pinout diagram. So ICs, while having the same functions, can come in a lot of different form factors. The actual semiconductor device is encased in what we call packaging. Now, this packaging comes in two main varieties, surface mount and through-hole. Surface mount packages are mounted to the surface of a circuit board. So you can see in this image here, we have this surface mount device, which is soldered onto the surface of the circuit board. These packages typically have small leads or no leads at all, and you will see when you look up ICs in the future that some common subtypes of surface mount packages are SOIC and SOP. Alternatively, you have through-hole packages, which have leads which stick through one side of a circuit board and are soldered onto the pads of the other board's sides. These leads tend to be longer because they have to stick through the circuit board. We use a common subtype of through-hole packages in our projects, and they're called dual inline packages, or DIP. And you'll actually find these a lot beyond just open project space projects, but many hobbyist projects, as well as professional applications. The benefit of DIP ICs, especially with prototyping, is that they can actually be placed on that middle channel of a standard breadboard. They fit nice and snug. It's a convenient location and allows you to access all of the pins through the strips on either end of the breadboard. Now that we've briefly discussed integrated circuits, let's talk about a specific chip, the 555 timer IC. Now, the 555 timer is a chip that's used as a timer, a pulse generator, wave oscillator, and an analog to digital signal converter. You're not expected to know all of these use cases yet, but just understand generally that the 555 timer is capable of generating different waveforms. On the right, you'll see what the DIP package looks like, which we'll use in this course. And you'll also see what a schematic symbol for the 555 timer looks like. In this course, the 555 timer will be used in what we call a stable mode to generate an oscillating digital wave, the waveform of which will look something like this. It is a rectangular wave that jumps between a high voltage and a low voltage. We'll talk about what high and low voltage means with respect to digital waves and digital signals in future lectures. So just bear with me right now, but this will become more clear down the road. Let's further examine the astable mode behavior of the 555 timer when it's used in a blinking LED circuit. Now, the function of the circuit is to cycle an LED on and off at a constant frequency. Now, the circuit's timing is going to rely on a component we haven't discussed yet. It's a capacitor. So we're going to pause and we're going to discuss capacitors right now. And naturally, we're going to talk about capacitors. A capacitor stores electrical energy, which it charges from a circuit and discharges back into the circuit. Now, the ability of a capacitor to store energy is called its capacitance, which is measured in units we call farads. On the right, you'll see a type of capacitor, which we'll use often in this course. It's the ceramic capacitor. Now, a ceramic capacitor is non-polarized. Some capacitors aren't, but again, for our typical use case in the course, we're sticking with ceramic capacitors, so you'll use the non-polarized capacitor symbol. Unlike a battery, a capacitor usually only briefly stores a small amount of energy. This is in contrast to energy-dense batteries in, say, your phones and laptops, which can discharge energy over, say, like 8 hours. A capacitor charges and discharges energy in the span of what could be milliseconds or less. Now, when a capacitor is connected to a voltage source, it actually charges until it reaches the same voltage as that voltage source. This is an important concept that we're going to use later to help you understand the 555 timer and the capacitor in our blinking LED circuit. Let's extend that capacitor concept just a little bit further to discuss a simple circuit with just one resistor and one capacitor in series. It's called a resistor capacitor or RC circuit. Now, taking a look at the schematic on the right, again, we just have one capacitor in series with one resistor. Now, I want you to imagine that this was an open circuit. The capacitor was disconnected from the resistor. We fully charged the capacitor ahead of time, and now we close the circuit. We connect the capacitor to the resistor. What will happen to this fully charged capacitor is that it will discharge its stored energy through the resistor. It will generate current. Now, the amount of time it takes to discharge that capacitor is dependent on the capacitance and the resistance. So the value of the capacitor and the value of the resistor. And this same principle is true for when the capacitor is charged by a voltage source. Let me break this down a little bit further. Don't get freaked out. There are numbers now, but I promise it's not as crazy as you think. So we have this formula. It's tau equals R times C. Tau equals the product of the resistance and the capacitance in the RC circuit. But what is this product? What is tau? The time it takes for the capacitor to climb from 0% to 63% of its full charge is actually the same as the time it takes for the capacitor to discharge from 100% to 37%. And the amount of time that takes is tau. The graph demonstrates this quite well also. So if we take a look at this increasing pink line, it represents the amount of time it takes to charge the capacitor until it reaches full charge. You'll notice as well that there's a second line, a decreasing line, which shows the amount of time it takes to discharge a capacitor from full charge to zero charge. Now, tau shows us the amount of time it takes to discharge a capacitor from 100% to 37% is the same as the amount of time it takes to charge from 0% to 63%. We're going to use this concept of tau to help us figure out the timing of the 555 timer. It doesn't quite add up yet because I haven't explained how the 555 timer works. But again, core to its function is that capacitor. Okay, let's talk about how it works. We have a complex schematic here, but we can break it down into some more readable components by going step by step through how this timer runs over a certain period of time. And what we want to focus on right now is that output pin, which is connected to an LED. Remember, the purpose of our blinking LED circuit is to turn off and turn on, cycle off and on this LED at a consistent frequency. And so when this capacitor here, again, this capacitor, which is core to everything else that the 555 timer does, when this capacitor is below 33% charge, the LED is going to turn on. And so again, when the capacitor is below 33% or 1/3 of its full charge, the 555 timer will turn on this LED. Remember that concept I shared earlier about how a capacitor will charge all the way to the same voltage as the voltage source it's connected to. When it's reached full charge, it will be the same voltage as the voltage source. That voltage source here is our 9 volts connected to the VCC pin. And so if the capacitor is below 1/3 of its full charge while the LED is on, that means its voltage is going to be below 1/3 of VCC. Now the next step is when the chip begins to charge the capacitor. The voltage of the capacitor is going to increase and slowly increase until eventually it reaches a threshold point. This is around 67% or 2/3 of its full charge. As this is happening, the LED stays on, but eventually that capacitor will reach more than 2/3 of its full charge, more than 2/3 VCC. When that happens, the LED turns off. The capacitor is now above 2/3 of its charge. It's now above 2/3 VCC. And as long as the capacitor remains above that charge, the LED turns and stays turned off. As a final step, the chip, the 555 timer, will begin to discharge the capacitor now. So the capacitor is now discharging from 2/3 VCC, from its 2/3 charge, back down until eventually it reaches the trigger point of 1/3 VCC, of its 1/3 charge. And when that happens, we go back to step 1. Now that the capacitor is below 1/3 of its charge, 1/3 VCC, the 555 timer turns the LED back on. And so now hopefully you can see this pattern of how the chip, again, the 555 timer is going to charge the capacitor up from a low charge to the threshold point. When it reaches that threshold point, the chip is going to turn off the LED. Now the capacitor is going to start discharging. And then when the capacitor reaches a low trigger point of around 1/3 charge, the timer will turn back on the LED. And so the LED turns on and off and on and off. The frequency of that process is determined by the amount of time it takes this capacitor to charge and discharge. So hopefully you can see how that concept of tau will start to tie back into our discussion of the 555 timer. So here we have a timing diagram. It's going to show you the relation of the capacitor charging and discharging with the LED turning on and off. Now, if we start from the left-hand side of the timing diagram where time equals 0, and we progress to the right as time passes, we'll see that again, the capacitor is going to start at a low charge. It's going to start somewhere below the trigger point or around the trigger point. Now, what the 555 timer will do, starting at the trigger point, is turn on the LED, set the output pin to a high voltage. The high voltage is going to supply enough power for the LED to stay on. As the capacitor charges now, the LED will continue to stay on this high pulse, and then the capacitor is going to reach the threshold point of 2/3 VCC, 2/3 of its full charge. When this happens, the 555 timer will turn off the LED, set the LED to a low voltage, and the 555 timer will also start to discharge the capacitor. And as the capacitor discharges, that LED will stay off until the capacitor reaches the trigger point, the 1/3 charge or 1/3 VCC. When this happens, when it reaches the trigger point, the 555 timer will turn the LED back on and it'll start to charge the capacitor again. And so you see this sawtooth waveform over time of the capacitor charging and discharging, and you can see it align with the LED turning on and then off. The time which the LED is off and the LED is on is loosely connected to our formula tau equals R times C. So hopefully now we're connecting the dots. We have a timing formula. This is, again, vaguely familiar. It changes slightly based on the construction of the 555 timer and where we place our resistors, but the essence of it is the same as our tau formula. Capacitance and resistance affect the charge and discharge rate of our capacitor, and in turn, that affects the time that the LED is on and the time that the LED is off. And if you look back to the schematic, we have two resistors whose significance is hopefully a little bit more clear now. These are the resistors which partly determine the timing of the LED and the 555 timer as a whole, along with the capacitor. So if we add the resistance of R1, this resistor, and R2, multiply it by the capacitance and this time constant, then we get the amount of time that the LED is on. If we take just the second resistor value, R2, and multiply it by the capacitance and our constant, we get the amount of time that the LED is off. And so if we wanted to change the amount of time that the LED is on and off, change the cycle frequency, all we would have to do is change our resistor values. If we increased R1, we would increase the amount of time that the LED cycles on. However, because R1 is not a component of the formula for the time the LED is off, increasing R1 does not increase the amount of time the LED is off. So if we increased R2, however, we would both increase the amount of time the LED is on and also increase the amount of time the LED is off. We could do the same with the capacitor. If we increase the capacitance, we would increase the amount of time the LED cycles on and off. If we decreased it, the LED would cycle faster. The amount of time it's on and off would be reduced. Now that we've discussed the 555 timer's functionality in this astable mode as it's used in a blinking LED circuit, hopefully it'll become more clear how these different pins work, which is why I've saved the discussion of the pin layout for last. So the pin layout or the pinout is something that you would often see in a data sheet. The data sheet would describe each pin, its function, its name, and maybe in the context of a specific use case. Because remember, the 555 timer has multiple modes. We're going to explain how it's used in a stable mode in a blinking LED circuit. So we're going to go step by step here, starting with our pin 8 VCC. That's our power pin. That's connected to our power source. This is our 9-volt power source. We have pin 1, ground. This is connected to the ground of our circuit. Let's say you connected a 9-volt battery here. You take the positive terminal of the 9-volt battery and connect it here in our circuit, and you would take the negative terminal and connect it to the ground of the circuit. Our last pin on this slide is pin 4, the reset pin. Here's what the reset pin does. It restarts the timer when it's at a low voltage. So basically, if it were connected to ground at any time, or whatever the ground voltage is, the timer would reset. Whatever the output is, it would be disrupted and the timer would start over. And so what we're going to do to ensure that the timer never resets, because it's not useful for our particular use case, the blinking LED circuit, is we will connect the pin to the 9-volt source. This way, the reset pin is always our high voltage, 9 volts, and the reset will never be activated. Here are probably the two most important pins on this chip. Pin 2 is our trigger pin. Pin 6 is our threshold pin. Now, trigger pin is going to turn on the output pin, turn on this LED, when the voltage across the capacitor drops below 1/3 VCC. Remember, that was our trigger point. And how does the trigger pin know the voltage of the capacitor? That's because the trigger pin sits at the same node as one terminal of the capacitor. So when the capacitor reaches 1/3 charge, 1/3 VCC, so has the trigger pin. And that's how internally the 555 timer knows when the capacitor has reached the trigger point. The same is true for the threshold pin. The threshold pin is going to turn off the output pin when the voltage across the capacitor reaches 2/3 VCC, when the capacitor reaches 2/3 of its full charge. Again, the threshold pin is at the same node as this terminal of the capacitor. When the capacitor reaches 2/3 VCC, so will the threshold pin. Okay, we're almost done here. The last 3 pins are pin 3, the output pin. Again, we talked about this briefly. It's going to output either a high or low voltage, so it's going to turn on or off the LED. This is where the digital waveform, that rectangular wave, is output. We have the control voltage pin. This can change the threshold and trigger levels, which we said are 2/3 and 1/3 VCC respectively. This is just by default. We're not going to change these. And so the control voltage pin is not connected to the circuit. Last pin, pin 7, is our discharge pin. This is what's responsible for discharging the capacitor when the output pin is low. And so the discharge pin is actually going to connect to ground and discharge our capacitor by bringing both sides of both terminals of this capacitor to the ground voltage. That's it. And so just as a reminder, you are very smart. You are very, very smart, but you are absolutely a normal human being if you don't understand the circuit just yet. And so I recommend you review the slides again, maybe rewatch the video, begin the project that accompanies this lecture. That is going to be what helps you solidify your understanding, what helps fill in the blanks, answer some of your questions about how the 555 timer works. With that, I leave you with another famous misquote. Thank you for watching. I hope you have a wonderful morning, afternoon, or evening, wherever you are, whatever time it is, and I will see you in the next lecture.